Those identify three covalent bonds you're going to have to remember. Now, if you get to Chem 2, you'll find that there's at least one more. But it doesn't involve 4 lines. It's something completely different. So, what you're going to be doing now is we're going to be looking at Lewis dot structures in certain atoms, Lewis dot structures in certain molecules. How do we go about figuring that out? So, let's take a look at some examples. Let's start with carbon dioxide. Now, the key thing about any of these molecules is identifying what we call a central atom. In identifying a central atom, you're basically finding the atom in these simple covalent compounds, which all the other atoms are going to bond to. And usually, it's the first atom mentioned. In the formula. However, there is an exception, and that is hydrogen. Since hydrogen can only bond to one other element, that isn't going to work. A central atom has to be able to bond to at least more than one atom. So in other words, 2, 3, or 4. And the maximum can bond to 4 because there are 4 valence electrons around carbon. So let's take a look here. So we have carbon here, and because it is in group 4A, it has 4 valence electrons, and that's going to put it north, south, east, west. Okay? Now, if this is the central atom, that means all the other atoms are bonding to it. Okay? So I'm going to put oxygens on either side. Again, it doesn't have to be done this way. As you maneuver things around and get a little creative, you might find that you don't have to put it in a straight line to get it to work, and that's fine. But generally, the Lewis dot structure must insist on north, south, east, west relationships, meaning you can't have one going off in northeast direction. It's got to be in this direction. Then, when we talk about shapes later on, we kind of ignore that. But when drawing Lewis dot structures, you try to keep it in north, south, east, west directions. Oxygen is in groups 6A as we talked about. So north, south, east, west. One here, one here. North, south, east, west, and I'm going to put one here, one here. And so what I'm going to try to do is now identify how many electrons the outside atoms are needing first. We don't look at the carbon, we look at the oxygen, and from there we figure out how many electrons they need in order to satisfy the outside role. Start with right one here. And you notice that you're going to have 6 electrons who wants to share 2 with the carbon. That now gives it 8 electrons for the oxygen. Okay? Now, you look at this and go, well, these aren't straight in line with the other ones like they were here. It's not a big deal. You can go off at an angle like this, or you put one like this and one like this, as long as you're showing the pairing. I'll do it the other way, the second way here. I'll show you that this still works. I really hate this board. It's no way. You have to love the smart boards. The dumb board. I got the dumb board version of the smart board. So there we got that pair right there. We got that pair right there. I hate it. That's still considered a double bond. It doesn't have to be, parallel to each other like these are here. As long as you show that you're putting 2 pairs of electrons together. And when you draw the line structure for this, go ahead and put your carbon there. You put a double bond there and a double bond there. Even though it is a nice neat double bond there, you still make a nice neat double bond here. You put your 2 oxygens there. And again, you can put your pair of electrons anywhere you want around it. This is just a representation, not the real thing. but it does help us understand how these things are going to be organized. So I like symmetry myself, so I'm going to put a pair of electrons here and a pair of electrons here, because that's what I like. And I'll do the same thing over here, a pair of electrons here, a pair of electrons here. As long as I have two pairs of electrons out here, I have to show two pairs of electrons here, but they don't have to be necessarily the same spaces as they were over here. Same thing here. I got north and east here, but I would maybe make it north and south there, and to me it looks better. But if you want to do the way that you left it, that's fine. There's nothing wrong with either one. So that is carbon dioxide. That's CO2. Okay? All right. Let's take a look at another compound. Let's take a look at ammonia. Oh, the board is so funny right now. Oh my goodness. Can't wait till I retire and destroy this board. Alright, so what's the central atom? Well, it's the first atom mentioned. And that'll begin. So M right here. How many valence electrons does nitrogen have? Well, you look at where nitrogen is in the periodic chart, and you see it's on number 5. 5A. Roman numeral 5A. 1, 2, 3, 4. Let's put it right there. Doesn't make it. Which is your 5th electron anywhere you want. Now, hydrogen has how many valence electrons on it? 1. It's in group 1A. So we're going to put the 3 hydrogens around the 3 singular electrons with the 1 valence electron facing that particular electron that it is across from. Okay? So we got this, we got this, we got this, because every hydrogen is lacking 1 electron to be full. Remember, you take care of the outside electrons, and then look to see what you have after you're done as far as the central atom. And it turns out here when you do that, you have 2, 4, 6, 8 electrons for the nitrogen, and 2 electrons for every single hydrogen. So the octet is satisfied for the nitrogen, and the duet corollary is satisfied for the hydrogens. So now we're going to write a linear version of this. Right, the ammonium ion, actually, that's what the ammonium ion looks like. This is ammonia with its 2 unshared pair of electrons on the left side. Again, you didn't have to do it this way, but you did have to do it in relation to the duet corollary and the octet will be satisfied. Okay? Alright, let's do 2 more. Let's take a look at methane, which is stage 4. So what's the central atom here? First element mentioned, carbon. And how many valence electrons does carbon have? Look for the A column number for carbon. And you see 4A, IB is 4. So we put 4 valence electrons around. North, south, east, west direction. And we put a hydrogen by each one. So after the circular Lewis dot structure here, we see that the octet will satisfy the carbon, 2, 4, 6, 8. The hydrogen is 2 electrons, so life is good for everyone concerned. We draw a linear structure for that. And that is what our methane looks like. Well, That's the representation, but that isn't really what it looks like. But it's the representation that allows us to know how they're going to distribute themselves around the central atom. So that's the circular, and that's the linear. Those dot structures. The last one we're going to do is cyanide. This is the formula for cyanide. Now, if you're not familiar with cyanide, cyanide is a very dangerous compound. If you were to consume cyanide, it would kill you because the nitrogen, which is normally a non-reactive element, becomes reactive in this covalent form, and your blood vessels, which normally would like to take the oxygen, will now take the nitrogen instead because it likes the nitrogen better and will never get rid of it. And so you basically stop or suffocate to death because when the process in the lungs where the nitrogen comes away from being consumed or gets positive and you start to turn blue because the compound with the nitrogen now turns blue instead of red. And then you see someone lying on the ground, looking all bluish, has blue lips, and smells like almonds. That person is dying of cyanide poisoning. His health is not dead already. It can be saved, but we won't talk about that right now. But the point is this, that if you were to eat almonds, you are actually consuming a very tiny amount of cyanide. It's healthy for you up to a certain point. Okay, so, question, what is the central atom? Well, you normally say hydrogen at this point, but that's the exception. Hydrogen is the exception. If hydrogen cannot be the central atom, and it cannot, then the next element after that is the central atom, and that would be carbon. Now, if it's a central atom, that means the hydrogen is going to bond to it, and the nitrogen is going to bond to it. So, we put in the electrons according to the periodic chart. Carbon has 4 valence electrons, because it is in group 4A. Nitrogen has 5 valence electrons, because it's in group 5A. North, south, east, west. And I'm going to put the 5th one over here. And hydrogen is going to be right here. And you don't have to put it there. You put it anywhere around there as long as it's either in north, south, east, or west. Not big northwest. So we'll start with the nitrogen, it only lasts one, so we're going to fill that up right here. Nitrogen has 5 valence electrons, like 3 to be full. So we have 3 pairs of electrons. And before we make the linear Lewis dot structure, we double check to make sure everything has 8 or 2, depending upon what the element is. Hydrogen has 2, that's good. Carbon 2, 4, 6, 8, that's good. Nitrogen 2, 4, 6, 8, that's good. So this is what it should look like from a circular Lewis dot structure point of view. The linear one, replace this to a single bond, and replace this with a triple bond. So H, single bond carbon, triple bond nitrogen, and an extra pair of electrons like this. Do not forget the extra pair of electrons in your structures. Make sure you have the octet rule satisfied in every compound. Okay, I will be looking for that when I see that. It's easy to overlook, especially when you're not used to doing this. So, your practice problems. These 2 atoms, you can draw write the Lewis dot structure just for that one atom, and the Lewis dot structure for these 2 compounds. Have fun.